are very counterintuitive. The more vacuum you have, the more energy you have. We'll discuss that. And so if you're adding, the larger you get, you put in more energy. That's the whole idea behind it.
So solutions that don't decay with are fine.
That can be a thing, but I don't remember. I have to say exactly what was the definition in the problem. What I had in mind. Better come to me afterwards. Okay, I do want to make two things before we start. So one, well done, somebody found a typo in my lecture notes in Einstein. That's something that happens once every, I think last time somebody found a typo, it was like maybe 6 years ago or something. So that's approximately the rate. Well done, I appreciate it. It's already corrected, of course. If you go to the course's webpage, it's fixed. Very good. And one thing that I did want to mention, I don't know exactly what was the problem here, but many people ask me about problem set number 4. There was a true and false part. So there was a geodesic, one of the things you were supposed to answer whether it's true or false is a geodesic is a path between 2 points in space-time that maximizes the interval distance ds squared. The answer is false, right? Now, but there's more than one way of seeing that. When many of you asked me, I said, okay, you asked, okay, but we did the max, we showed it's an extreme, we did not show it's a minimum. Which is what? Right?
This is the Euler-Lagrange.
Yes. But there is something which, but then I told you, okay, look at the physics there, really. One thing that when I wrote this thing, it's been a while ago, that I had in mind was, okay, I mean, you have space-time geodesics, but you also have time-like geodesics. Time-like geodesics is what you have if you have particles that move faster than light. And then there will be the opposite. Okay. When we talk about real-life particles, like particles that only move slower than light, which is us, basically, of course, we'll have that it's going to be a minimum. When we have a space-like geodesics, will be particles that move faster than light, will be a maximum. That was my point. Anyway, I guess that's one of the things that there is a difference between the mathematical derivative and the physical interpretation of what it is. Physically, what we have is, the geodesic, the way we define it is the shortest path. Yeah.
If we have a sphere like with Earth, and we want to go from point A to B, we can do it like in 2 ways, in the short path and in the other direction. So both of them are
it's sort of a yes and no, right? Because I can say that the point from A to B here, right? I can go like that, but I can go in. It's going to be infinite, right? I can go like that. It's still a path. It can be infinite.
It's not satisfied with the geodesic equation.
Yeah, you're right. That, but the sphere, sphere is a specific example of a closed space. Space doesn't have to be closed.
Yeah, but to say the claim is false, you have to give one example.
Basically, yes. Okay, you can use that as well. All right, the idea is, okay, I guess this is the difference between, again, as I said, the way I think of it, right? Between the mathematical derivation and the physical interpretation that you give to it. All right, so that's the comment that I wanted to give. Yeah.
There is a more physical example to think of. So you drew the points A and B. Yeah. Imagine that above them there is a point C, where there is something massive like a black hole.
Yeah.
Now, the light can move from A to B in a short path, but it also can move around the black hole and then come back to B, both of which are geodesics.
In principle, yes.
So one is shorter than the other, and that is a realistic situation.
That is a true situation. And you can also sail around the globe, right? What he says is correct. You can go from point A to B into a different path. Okay, I guess I have to think a little bit more of what would be the precise mathematical physical answer. Anyway. Okay, so we're talking about Schwarz's solution and black holes. So we derive trajectories in Schwarz's metric. We spent a lot of time, last lecture was about what type of trajectories we can find. And then we started to talk about classical tests of general relativity. So now there is a point in going back to all the types of trajectories that we can derive. The important thing was that we could make the equation of motion, we could write it in the same way as we did for an equation of motion, with a term that looks like a potential. It has it has 4 terms, right? But the first 3 terms were identical to the Newtonian potential, and it was only this last term, the 4th term, which is different, and that makes all the difference, especially when we get close to the Schwarzschild radius, 2gm over c squared. And then we started to talk about classical test of GR. And I stress time and again that this is a department of physics. We're learning physics, and essentially physics is an experimentally based science, which means that everything you said has to be tested experimentally, and if it is found valid, we accept it. If it's found invalid, then we don't accept it. And I mentioned 4 tests. Actually, there are 5 tests today, which are independent of each other. So the first one is the gravitational redshift. The second one was the deflection of light. By the sun or other stars. The third was a precession of the perihelion. Yeah, I got a bit shocked that I didn't know that. So I went back to this book by Jackson, sorry, not Jackson, Goldstein, and I looked at the derivation it does there. It's not that problem. That's small. Let's take a few pages and then you should do it. I thought that if I have some time over the weekend, I'll sit down and type it for you, so I'll just give it to you, or maybe one of the tutorials maybe you can do about that. But it's really just me finding the time. The problem is that I'm so busy, you got no idea. It's going to be very, very hard for me to find the time to sit down and type it, even though it takes like 2 hours to do it. But then again, you can do it yourself also. These were the 3 classical tests that were proposed already by Einstein himself, after writing his equation and knowing the solution. The 4th one is gravitational time delay. Of light that is going in gravitational potential. That's also known as the Shapiro time delay, after Irving Shapiro suggested that in the 1960s. And I can add to that the 5th one's are gravitational waves, which is something which in the past 10 years became reality. Although it's been anticipated actually very early on. I think first Einstein realized that you can get gravitational waves, I think 1917 or something like that. But it took 100 years for the technology to mature until people could actually see that.
How do you measure all these?
What?
How do you measure all these?
How do you measure what?
All of these. Don't these effects, aren't these effects so small?
No.
They need very, very large masses to get them.
That's what I said then. Everything has been measured. It's not just some theoretical predictions. Everything that is written on the board are things that have been measured.
Yes, how?
Okay, let's go one by one. So first I explained to you that we had time to explain gravitational redshift. Right?
The absorption.
What?
absorption, because of the absorption losses.
Exactly right. So gravitational redshift, we said that it was basically, we already said it twice, right? Once we said it when we discussed the weak field approximation. That was one of the starting point at the beginning of the semester. If we go back now, it looked very simple to do. And then we said that omega 2 over omega 1 is 1 minus 2 gm over R1 divided by 1 minus 2 gm over R2 to the power of 1/2. Or 1 minus gm over R1 plus gm over R2. Now you ask how this is being measured in reality. Well, that's quite simple, right? We look at how do we know what is the composition of the sun, for example, or stars? Right. We look at the spectrum. Now nobody is going to probe the chemistry of the sun, right? But we see the spectral lines. Now you know about spectral lines, right? Yeah, that's supposed to know about it. There is a course in spectroscopy, but the first place you're supposed to see that is in modern physics, whatever they call it. Right. So there is spectral lines which correspond to different elements, right? And we identify the same spectral lines in all other stars, basically. We know that the stars all have the same composition, roughly. I mean, there are different types of stars. Basically, all of them burn hydrogen to turn it together, except special stars, white dwarfs or others. So we identify the spectral lines, but the spectral lines, right? So we have an emission source of emission comes from the star itself, and the observer is sitting somewhere over here. That can be even our own sun. And you'd see the same spectral line, which you can identify, because there are several lines. Palmer, Ashen, and all this.
These are absorption lines, not
Yeah, these will be absorption lines, obviously. But it will be the same frequency as emission. Which I don't know if you did this in a lab. I think I did it once. I mean, you can take various chemicals and burn them and look at them in the spectroscopy. Did you do that? You don't need to open a discussion. And mercury is actually very.
Plug in some lamps into
put some lamps. We actually pour some. You can try pouring some of. Don't do it with mercury because it's poison. Other things you can do. What?
Is it very, very poisonous?
Mercury, no, very poisonous. Don't do it with mercury. You can do it with some other things which are less dangerous.
Hydrogen.
What?
Hydrogen.
You cannot do it with hydrogen. What? What? leak בסדר, לא משנה. מוביל אותו בכל. לא משנה. So it's a nice experiment which I'm not sure you can try it at home, but not sure if I tried it at home or not at a certain point. But never mind. You can try it in the lab. We have some lab. נכון, אתה צריך שיהיה לך ספקטרום. That's right. You can do it with the salt, but you have that you use spectrometer. So you just need to put your hand in the spectrometer and then you can try it. Anyway, we're not going to talk about spectroscopy right now. You see these lines, and you see these lines are being shifted, and you see that from the sun as well. Okay. So this has been measured. That's one thing. The second thing is the deflection of light by the sun. So let's discuss that now. What does it mean, deflection of light by the sun? So historically, this was the first suggestion for independent test of general relativity. In fact, if you know, this is how Einstein became famous. Right? So he wrote that. Who knew about that? Right? Who read this article anyway? What does it mean, deflection of light by the sun? this is our sun, right? And this is us. This is Earth. It's blue. We are circling the sun once every year. And what do we do in the night? What? Homework. Homework, that's good. Better than sleep. And some of us go out and watch the stars. And then we're watching the stars. We have stars here. You can look at the sky, and the sky are full of stars. And I'm sure that you've noticed that if you look in the different seasons, the stars look different. Right? Why? So you look at different parts of the sky. Like you look at here. You have your skies. Let's say this is the summer, this is the winter. So in the winter, the dark side is here. In the summer, the dark side is here. You're seeing different stars. Right? Now, what is deflection of light? What does it mean? So, if you are here in the winter, let's say, and you look at the sky, right, then the sun will go, light will go in a straight line. So you put a plate, take a picture of the sun, of the sky, and you see the stars will be on your plate, right? Camera. Then. Now half a year later, you want to do the same trick. Now it's a bit more tricky because so you put the what? Right. So it's a bit tricky for various reasons. Now what's going to happen? What? The light is going to go from the star. Straight lines. But when it's going to go close to the sun, what will happen? It will be deflected. Right? Same with this guy. Will be deflected, and with this guy, which will be deflected, but slightly less. Now you take the plate and you take the picture of the stars. Now we're not going to see anything. Why? Because the sun is too bright. So what do you have to do? You block the sun, right? So how do you block the sun? Naturally, the thing that will block the sun is if there is a lunar solar eclipse. This is a natural way of blocking the sun. But otherwise, it's going to be very difficult.
First light switch.
What?
First light
I don't know of any switch that you can turn on and off the sun. Fortunately, if there was something, some idiot would surely try. Right? So if there is a lunar eclipse, this is the moon, right? That happens to be such that exactly in the right location that it blocks the sun. Then you can take you have a few minutes where you can take a picture of the stars. And then what you do is just compare these two pictures. And what do you see? The stars are not exactly in the same position on your plate. Right? Why is that? Because the light, as we said, the light moves at straight lines, but it's been deflected when it gets close to the gravitational potential of the sun. So let's do at least some sketch of this calculation. Gravitational waves I will not talk because it's a subject by itself. So maybe if I run fast, I'll have like one lecture at the end. But I don't think one lecture is enough to give you full mass. Full mass definitely not. 2 or 3 weeks to give you. Maybe, I don't want to rush, maybe I'll say a few words about gravitational waves. It's a chapter, right? This I'll say a few words now. So we have a light ray that approaches from infinity. And then we have, so remember we had 1/2 the r over the lambda squared plus v of r is equal to 1/2 e squared. V of r it's a light ray, then epsilon is equal to 0. We had half epsilon minus epsilon gm over r, but this is 0. Plus L squared over 2r minus gm minus gm L squared over r cubed.
Supposed to be r squared.
R squared. Of course. So if I plug it in here, V of r, and I divide by L squared, multiply by 2.
So shouldn't there be another term in the denominator of the r squared?
What? No. That's all the terms we have. No, we derived these two equations the last time or the time before that. 1/2 the r over the lambda squared plus v of r is equal to half e squared. V of r is, we had 4 terms. The first two are 0 for massless particle, which is a photon. And then we're left with these two. L squared over 2r squared minus gm L squared over r. That's fine. Plug it in. 1/2 the r over the lambda squared plus L squared over 2r squared minus gm L squared over r cubed is equal to half e squared. So I multiply by 2 over L squared. And I get
the units don't add up because there is a kilogram squared in L squared, but in 2r squared it doesn't have mass. And the left hand
per
side
unit
is
mass. Everything is per unit mass. It's per unit mass.
Oh,
Normalized mass. So we have the r over the lambda squared, 1 over L squared. Guys, these are actually important points, right? Because there are a lot of delicate points here. Make sure that you review the things. Things are clear in your mind. 1 over L squared, the r over the lambda squared. Plus here I have 1 over r squared and 1 minus. I multiply by 2, so it's 2 gm over r. Is equal to e squared over L squared. So I'm now defining what's known as the impact parameter. B, which is E over L. Sorry, L over E. My apologies. And I use L is r squared d phi over d lambda. And we get from this equation d phi over dr is plus minus 1 over r squared 1 over b squared minus 1 over r squared 1 minus 2 gm over r, all that minus 1. Now let's draw it so just that you make sure that you're fully with me. What do we have? So the x-axis. The light ray comes from here. This is the source of gravitational potential. This is B. This is the impact parameter. So in real life, what's going to be the impact parameter? Like in that experiment? What will it be? Be the radius of the sun. So we cannot not have reflection of light inside the sun, right, from stars. Right? It's a minimal impact parameter. You're right. Now,
This is the scale. It's much larger than.
essentially yes. So, wait, hold on. So what do we have? We have a scattering process here, right? So the photons come from here, and then instead of moving in straight line, it will make such a deflection, and then everything is highly separated. This is R. This is phi. And if we take the asymptote, parallel, then this is the deflection angle, delta phi deflection. Right, the picture is clear. What happens here? I'm taking a light ray. It's the same. The same cartoon that is drawn here is drawn here. I have a light ray. The light ray travels, and then has to follow this. This equation, and then just plug into this equation. Do a little bit of mathematical manipulations, which are pretty straightforward, and I get an equation that tells me how the phi changes with r. And what is left to do, if I want to get the maximum deflection angle, delta phi,
Integrate this.
I just have to integrate that.
Minus
Exactly. Or, the way it is classically being done, you're defining the minimum radius. This will be R1. And then you're just integrating twice from R1 to infinity for a light ray that starts from infinity and ends up at infinity. And then of Vr times that. So Vr over R squared times what's written here, 1 over B squared minus 1 over R squared, 1 minus 2 GM over R minus 1. So, it's a nasty integral, but it's definitely doable. There's nothing unique or special about this integral. And as we said, the impact parameter B, there is a limit here. Like in real life, we have that B must be greater than the radius of the sun. Which is something like 7 times 10 to the 10 centimeters. Which means, if I go from here, that means that 2 GM sun over R B squared, R C squared, over C squared V has to be smaller than something like 10 to the minus 6. So the deflection is actually very small. Practically, when it comes to the sun. Do you follow what happens here? Okay, now there is a solution. The full solution is given in the textbook by Hartel, which I didn't bother copying it because you can simply go to the textbook and see how Hartel solved this equation. Because of the smallness of this parameter, it's doing it in a perturbative way. Basically, a Taylor series in GM over B. And the solution, I'll just give you the final result. The solution is delta phi is approximately pi plus 4 GM over B. Just to make sure delta phi is, definition is that. So the pi is what you get without, and the real deflection that you get is 4 GM. course, c squared here if you want to put the real units. That's a very small, right? This is less than 2 arc seconds. Right. You know what is an arc second?
It's
1/60.
1/60 of an arc minute. What is an arc minute?
1/60 of 1 degree.
What?
1/60 of 1 degree.
I think it's an arc minute.
Arc minute is
1
1/60.
degree. Okay.
Yeah, it's quite small.
Yeah, it's small. So this is smaller than 1.75 arc second. This is the single arc second. It's very small. Okay. But I'll report something which is amazing what you can find on the internet. It's a bit old now. What is that? It is being shown here.
One on top of the other, the 2 slides.
So in order for it, so the first, to get this technologically, what you need is to compare two plates, right? So at the end of the 19th century, photography started to become widely used. Astronomers really liked photography. Like before that, you could, when you look at the sky, you can just draw it what you're seeing, which is of course not that accurate. But once cameras become technology advanced, and you start to get cameras, and you start to have these plates that you just put the telescope, you connect it to a camera, a very old one, and then you put this on the plate, and then you have these plates, films it used to be called. Maybe it was before your time, just used to digital cameras. I still remember the films the word. And then again, so this is first plate was done here. And then this is the famous expedition led by Arthur Eddington in 1919 to somewhere near the equator of the shores of South America, because there was the solar eclipse, which was full at the time, and then he took the second image of the same location in the stars in the sky. So one was here. He had one half a year earlier. He had one here. And then when you put them one on top of the other, that's roughly what he got. And what you see are these, these 2 dots really represent the same star. Only being shifted. And as you go away, further away, then you have the deflection, of course, is lower and lower. Right? So further away from the source of gravity, then it gets less and less deflected. Okay? So after that, people saw that and realized Einstein was right, because there is no way this could be explained in Newtonian mechanics. Yeah? Yeah.
What about the movement of the stars?
Motion of the stars?
Yeah.
Relative to us, they're fixed.
Otherwise?
Relative to us, they're at infinity and not. Now, so this was done. Yeah.
To explain it with just saying that photons have mass, or effectively gravity with mass, like they
No,
have mass.
photons don't have mass.
But can you explain it with another model that says photon has mass, which equal to their energy over c squared or something, and they just this is their gravitational mass or something?
I mean, alternative theories.
It's probably also says
They will fall, they will not obey then the Michelson-Morley experiment. And then you run into a speed of light which changes this photon's energy, which you don't see. That means that different photons at different energies will arrive to you at different times. I'm sure this has been tested experimentally. Speed of light is known.
Speed of light was never measured. Only the
Speed of light was measured.
Was never measured.
Speed of light was measured.
Only the two-way speed of light was measured.
I mean, one way.
Well, yeah, the one-way
I'm
speed
not-
of light was never measured. Even though the
No, you're wrong here. There has been, but this is something which is reasonably recent, so that's definitely not going back to that times. We know that when we have explosions, for example, of supernovas or stars that explode, we do measure different arrival times and different wavelengths. People have written papers about it, showing that photons at different wavelengths arrive to us at the same time.
not saying that. I'm saying that the speed of light is never measured as a number.
It's a number.
The one-way speed of light.
I have to look at that. I don't know. I cannot tell you that you're wrong right away. So since I don't know, I better not comment. What about that? What do you see here? That's of course a much newer image.
See it as stars, ledges.
Yeah, it's not exactly stars what you see here. This is called Hubble Deep Field. Right? This is a Hubble Space Telescope, and deep field means that it just pointed this telescope somewhere in the sky and just let it stare there for a long time. You know, and since this is this is CCDs, right? This is modern technology. You know CCDs, right? This is how your cameras work. You don't have films anymore. This is Charles Chaplin devices. This is how modern cameras work, right? You just collect photos. Basically you're counting photons. So the longer you stare at a location, the more photons you'll see. What? Sorry?
Don't modern cameras use CMOS?
Some maybe yeah. Some do, but these cameras definitely Hubble uses CCD. That was maybe this technology already changed a bit now, but I think it's mainly in astronomy it's mainly CCDs for various reasons. These are not really stars. Maybe the only star around here may be this one that you see because of this lines that you see. This again, this is not real, of course. This is coming from the detector. What do you have here is something which looks very similar. You look at very distant galaxies. So you have galaxies, and the galaxies do tend to come in clusters. And so what you have is something that we are here. We have several galaxies around here, and then galaxies they are all over. So you also have galaxies very far. So you have some galaxy here, elliptical galaxy here. Now the light of this elliptical galaxy, it's traveling through space and time. What happens when it gets close to the gravitational potential of that cluster of galaxies? It will be met. It has to. So it will be going like that. And if it goes from here, it will be going like that. Now, if this was an exact, so it's on the same line, and the potential here would be exactly spherical, what would you see? A circle, right? It's a ring. So it has a name. That's called Einstein's ring.
It doesn't have to be if it's exactly on the space.
Exactly on the space.
And then an ellipse.
No. It will be a ring. So we go from all directions.
No, but if
it's a point source essentially.
But if you're not on the straight line, if you're slightly above the axis of the sun.
If you're slightly above, what you see is a keshet, part of a ring, arc, which is what you're seeing here. And if you look close enough, you'll see that arc comes from the different from the other side as well. It could be in slightly different radii. Depends how far above or below you are from the. So this is called lensing. This is gravitational lensing. What you're seeing, of course, life is not always so simple, so you don't see these full rings. It's very rare that you see these full rings, but there are several examples. I just didn't took the picture. And what you can learn from this is really about the source of the potential, mainly the gravitational potential here. So you can measure basically the masses of these galaxies using that.
Question.
Yeah.
It's about something you said earlier about the way sun bends light. And okay, so if we look towards the sun, then the light from the sun is more intense, so you need to wait for the solar eclipse, right? What if you try to measure light in frequencies that the sun doesn't do? You try to observe something that it's something above ultraviolet, and then
the sun is a black body, so it doesn't. black body spectrum, which is all over. And it's many, many, many orders of magnitude above the other stars, which pretty much emit at the same wavelengths. So it's not going to be very useful.
But it's not the sun that hides the stars. When you look now, you don't see the stars. It's not because of the sun. It's because of the air. It's because of the
Essentially, it's because of the sun, right? The sun, because it's so bright, right? The light rays from the sun are being reflected from the Earth's atmosphere.
Yeah, take out the air and you don't have a problem.
Well, you
if
still
you're
have a
on
problem.
the moon and you look
You
at
have
the
to-
sun, it's
well,
just
It's a practical problem, right? You know, because if you have your sun, if there is no air, you're right. If we're on the moon and we're looking slightly away from the sun, we'll have a much less of a problem. We'll still have a problem that if the sun is even in a small part of our CCD, it will basically destroy it. Because there are,
no, you could hide
contrast.
it with
You have to hide it.
No, with an object. You don't need to hide the whole sky.
In principle, yes.
So
Yeah.
what I'm saying is that the black body radiation that the sun emits is not important to hide
No, it is
radiation in other, because what is important is the radiation of the sky, and this is not black body radiation.
It's a scattered black body radiation.
Sorry?
It's a scattered black body radiation. You're still seeing the sun. It's already scattering inside in the atmosphere. That's why they look blue. But in case you're wondering, it's not
they
the
look
ocean.
blue
Right?
because the blue is scattered. It doesn't mean that
The blue is scattered more. Right? Red would be
air scatters
that's
everywhere.
narrower. That's why the sunset is red. Right? But again, we're talking about 12 orders of magnitude in brightness to what you see from the sun and what you see from the stars. So practically you need to hide the sunlight that you can see something. Just we don't have this dynamical range of one detector that can detect so many orders of magnitude difference in brightness. Okay, but this is more engineering department of how to do this. You get the idea of how these things work? That's important for me, that you get how these things work. You can basically do that, solve this integral, get this result after doing a Taylor expansion. It's doable, and then, of course today you can do it numerically. But again, this has been done more than 100 years ago. So this is deflection of light by the sun or other stars. So this is called a lensing. There's also microlensing, which is a little bit more. It's a field by itself. The idea is essentially it's the same physical concept. Okay, we said that there are a few independent experiments. So we talked about two. Let's talk about the third and the fourth, at least briefly. And the rest now. So the precession of the perihelia, right? So to remind you, right, all the stars around the sun are moving ellipses. So there is an inner radius, there is an outer radius. All the stars, of course, it's highly exaggerated, and the true motion is an ellipse. But this ellipse is not repeating itself exactly, but there is a slight deviation. So if we follow the true motion of the stars, move like that. The full description, so this is called perihelia. This point here, closest approach. And the motion that does not repeat itself, right? So there's this type of motion. This is called precession. And yeah, this is notes is Euler's time. So the 19th century physicists knew everything they need to know about precession. And during that time, the measurements become accurate enough, so they had very accurate measurements of the location of the inner planets of the solar system, Mercury, Venus,
Inner planets.
closest to the Earth than closest to the Sun than us.
No.
We are the third planet of the line, right? Yeah. Mercury is the first, Venus is the second. Right? We are the third.
Yes.
Then there is Mars or others. Okay.
But this effect affects Mars. All the stars.
That affects everything. Where is the maximum effect?
Close the sun.
When you're closest. Obviously, right? What is the origin of this effect? It's extra term in the potential.
Gold.
What?
Which gold that are bigger.
Yeah, of course. When R gets smaller, the effect gets larger. It's very simple. So easier to find it when you look at the inner planets. Also, the inner planets rotate around the sun faster. Right? If you go to, I don't know, Jupiter ends up one circle around the sun in something like 200 years or something. So you don't have that many accurate measurements. Inner planets rotate around the sun. Their year is shorter than ours. I think Venus is 200 something days. Mercury, I don't know how many days exactly. This is something you can easily find on Wikipedia. Okay, so right. So if you go back to historically, right, Einstein knew about these measurements. So you can say that this was a post-diction of the theory. I mean, the first thing maybe, I don't know exactly, but when he wrote the theory, he could calculate that first thing, and he could see that the theory predictions match what we're seeing observation about the precession of the perihelion of Mercury. There was a deviation of.
But he needed the Schwarzschild solution.
Well, 1 year afterwards, it was Schwarzschild solution. There were various theories about how to explain planet X. Hear about it, planet X? What? Planet like Earth that is in exactly the opposite side from the sun. Right? Maybe there is another planet rotating the sun like us, but
we have
exactly.
Okay. But
We'll never see it.
But we have telescope.
If it's exactly behind the sun, you'll never see it. Regardless what
We have
telescope.
telescope in space that are not.
Where do you put telescopes? Even if you put them on the moon.
No, if Hubble.
If you have a telescope now that is Hubble is rotating around the Earth, 400 kilometers above the Earth.
Other telescope that are not protecting the Earth.
Don't worry, there is no planet X. It's good for science fiction. There was, I think it was Euler that showed that this is if, or Lagrange, showed that if there was a planet X, it would be unstable. If ever in the history of the solar system there was such a planet, it's long been. So it's unstable.
Why exactly? Because of the other planets?
Yeah, because small stability is something which I'm not supposed to teach you here, right? So if you make a small perturbation, it will go away from the orbit.
But what about the three-body problem and the way the magnetic is unsolvable?
This is not GR. You can do that, and it's a different course. Okay, three again. No, I don't think you do three-body problem in classical mechanics. Just this is really good. It's fun, but it's way too simple. Okay. So again, the calculation is essentially the same thing for the line deflection, right? Just for massive particle. That's all, right? So it's the same. And again, two textbooks I know of. One is by Hartel, one is by Carroll, and I would advise to look at Hartel because I think it's doing it in a more accessible way to the students. We give the full solution. I'm not going to give you the full solution because it's just writing down the same equation and then solving it in the perturbative limit, just doing a Taylor expansion using the first term. So for calculation is the same as deflection of light. Only massive object. There's nothing fancy here. So look at Hartle, and you find out that delta phi precession, this is just the final result. Hartle, delta phi precession is 6 pi gm over c squared a 1 minus epsilon squared. A, semi-major axis. And epsilon, eccentricity. So it's just maybe a note. And obviously the effect is, these are both in the denominator, so the effect is largest for small a. That's why you want to get the inner planes. The predicted value, 43 arc seconds per century. Very small. But at the end of the 19th century, when you have accurate enough measurements of mercury from the beginning of the 19th century. So by the end of the 19th century, it was already okay. The last thing I want to mention, questions about that? I didn't say too much, not too much to ask. If I have time, it's a very big if, because normally I simply do not have time. Let's see if I can do some ordered derivation of what is a precession in classical mechanics, just to compensate for you. Yeah?
Is there any other example of precession in the universe of something that moves around a massive body for a long time?
Moon around the Earth. What?
We measure them first.
Of course. But it's going to be less because the gravity of Earth is very.
It was measured or just?
It was measured, but the effect is going to be much less because the mass of the Earth is much less than the mass of the Sun. You can do it in the lab. Laboratory experiment today. So last thing is the Shapiro time delay. And again, it's based on the same principle for the Shapiro time delay. Told you I happen to know Irving Shapiro in person. He's a great guy. Somewhere around 90 today. Healthy and happy, as far as I know. And you do the same thing, but rather than for solving for the phi dr, you solve for the TDR. Use the same equation exactly, and you solve for the TDR. It's actually the same equation, right? Just using so same solution, and use 1 minus 2gm over r dt over d lambda equal to e. Plug into the same solution that we just derived for the light reflection, and you end up that the TDR is equal plus minus 1 over b, 1 minus 2gm over r minus 1. And that is the same solution. It's the same solution, 1 over b squared minus 1 over r squared, 1 minus 2gm over r minus 1. What does it say? Again, we are the Earth. This is the Sun. We are the Earth. We are orbiting the Sun. Right, Earth. Then what do? We want to send a signal and look at the time it takes to get back to us, right? How will it get back to us? Sending a signal is okay. How will the signal get back to us? What?
Reflection.
Reflection by what?
Maybe curving around.
Maybe if you send a signal, you can
Well,
keep
this
it
is
like
some
get
air
it to the
space.
other
Only it goes
side.
to the, it will go to the other side, only it will go, at the speed of light.
Maybe put some mirror on the other side. Or black hole.
We can wait for planet X.
Like this. Yeah, a little bit more realistic suggestions.
Maybe we can just put some, I don't know, some astronaut over there.
Put an astronaut.
Yeah.
We're here.
Uh,
Poor guy.
maybe. No, not that close to the sun, but
Yeah, rather than astronaut.
Is it better from other planets?
Yes, we have other planets, right? So we have Venus, for example, is orbiting. This is a little bit Venus, right? So Venus is orbiting the sun closest to us, right? So that means that the circle of Venus is not the same as ours. So at a certain point, Venus is closest to Earth, and at another point, Venus is further away from Earth, right? So what do? We send a signal, right? The radar signal. And partly it's deflected from Venus and go back to us, and we can measure how long it took. And we know to calculate the time from Newtonian physics, right? And then we wait enough until Venus gets to the other side of the sun. We send again the signal. Again, it's being deflected from Venus.
but you won't be at the same
No, it's
place.
okay. We'll be here. Venus will be here. So it's fine. I'm just lazy. Right. So we'll be somewhere here. Venus will be somewhere here. Important point is that at a certain day it will be closest to us, and if you wait the order of half a year, maybe more, maybe less, it will be on the other side, be further away from us, on the other side of the sun. And then the signal that we send will have to go closer to the gravitational potential of the sun, back and forth. Right? The typical time when you measure it, the typical time that it takes to get Venus back and forth for a signal, right, that travels at the speed of light, is this will be a few minutes. The time difference we're talking about here, a few microseconds. That's the time. So it's a very small time, very short time. But apparently, in the 19th.
Microsecond, isn't it like in the scale of the error of the location of Venus?
Apparently not. So the delta t axis, so I'll just give you the final result. So the delta t axis is 4gm over c cube log for a r Venus times r Earth divided by r1 squared. R1 would be the b, the closest approach to the sun, plus 1.
That means that we need to know the location of Venus for with an error of less than kilometers. So
Yeah, we do. Turn out. Sorry, it's not me. It's my mistake. It's not. It's not microsecond. It's hundredth of microseconds. Time, and these are the results that you can see. I don't know if you can see. It's very small. I'll put it when I put my lecture notes, so you can see. This is a real measurement. It took 2 years to make these measurements every day, and you can see that. To speak, and the feet, of course, is what you'd expect from the Shapiro time delay. So obviously it works. Yeah, this has been done in 1970, so more than 50 years ago. So once when Earth and Venus the same side, and when Earth and Venus the other opposite side. That's it. Conceptually, you got the idea? Okay. You will get in homework to do some calculations of the type, so that you can actually feel that in your hands. All right. More questions? No. So, if no questions, then we erase the board and move on. now, we're going to learn about black holes. The real thing, the truth behind the myth. Again, so far, everything we discussed was about trajectories of particles that move in the Schwarzschild metric, but away from the Schwarzschild values, radii which are much greater than 2gm over c². As I said, and I say it again, this is the only thing that is relevant when we discuss motion for the solar system. Okay? Because solar size is way bigger than the Schwarzschild radius. You'll never find anything related to that in the solar neighborhood. But there are objects which are so compact that their size is smaller than the Schwarzschild radius. We call this, we did not define yet the black hole, but I take it that intuitively you know what I mean. So I'm going to use this term even before we fully define it. So let's see what happens. I'm going to write down the Schwarzschild metric. ds squared is a minus 1 minus 2gm over c² r. C dt squared plus 1 minus 2gm over c² r and minus 1 the r squared plus r squared d omega squared. And I'm considering now a light ray. Consider light ray that propagates radially. Why? What does it mean radially?
The omega squared is
Right. Radially, just in the radial direction, so theta and phi are fixed. Right? So I don't care about that. What did I, when I say light ray, what did I mean?
ds squared.
ds squared is equal to 0.
We did it in the tutorial. Something similar.
Okay, good. So ds squared 0 is a minus 1 minus 2gm. Okay, let's remove the c squared r dt squared plus 1 minus 2gm over r minus 1 dr squared. So let's just try to solve that, and I get that the t over dr is a plus minus 1 minus 2gm over r minus 1. R What happens at large R? What is the t over the r?
Plus minus 1.
Plus minus 1. So if I draw that, large R, plus minus 1 would be 45 degrees. Right? dt over the r is plus 1. dt over the r is minus 1. We simply said that radially it can go which direction? Either towards the black hole or away from the black hole. Plus minus 1. What happens when I get closer to this, like this, when R is not infinity? What about T over the R? Starts to shrink. If I get closer, do something like that. What happens when R equals exactly 2 GM over C squared? It's what? It's infinity. It's infinity, right? T to the R. No, it's infinity. 0, 0 minus 1 is infinity. Now you understand what happens here, right? So if I have a light ray, and the light ray goes from infinity, approaches the black hole. Right, so here it goes, no problem, no problem. What happens when it gets here? It gets close to the black hole. If I have to draw it, you go like that. This is time, right? This is the time axis, this is the R axis. So what does it mean, right? You cannot get there. It will never reach the black hole. Right? Right. What?
In these coordinates.
True. But, what's wrong with these coordinates? There's nothing. So, when for R goes to infinity, then the T over the R is plus minus 1. When R goes to 2 GM over C squared, the T over the R approaches infinity. Plus minus. So a light ray that approaches the black hole never seems to get there. And of course this is an illusion, right? A light ray or any other massive particle, astronaut or probe or whatever, that is being sent to a black hole will reach there within a finite proper time. But what does that mean? You just derived?
So someone far away will never
For
know.
someone far away will never see that. So let's say that you're here in a spaceship. You're sitting here in a spaceship, and you're sending a probe into the black hole, right? And the black hole, the probe sends you a signal once every whatever. Like, I don't want to say there is another stupid astronaut that decides to get in, so let's say there's a probe that sends you a signal, and say, okay, I'm here, everything is fine, so it sends you a signal, and now that it's here, it sends you a signal, it sends you a signal. What are you going to see? You're ever going to see it approaches? Never. You'll never be able to see this probe get into the black hole or crossing this Schwarzschild radius. What
signals will be slower and slower.
Right. Signal will be slower and slower. So it's okay. Everything's okay. Everything's okay. Everything is okay. Also, they will become redder, right? Because of gravitational redshift, they will get redder and redder. Send you some photos, they're redder and redder. So again, you're never, as an observer at infinity, you're never going to see anything crossing the event horizon. It's not going to happen. It's quite cool. But, of course, things will cross. So that thing is, an observer at infinity, which is we, never sees an object crossing the Schwarzschild radius, RS.
You say that it will get there, but isn't that an example of something that happens in one reference frame but doesn't happen in another? 'Cause
In a sense, it will get there, in a finite time of its proper time.
of his proper time.
Yes. So if I'm an astronaut and I say, okay, I'm going to go there, I want to check what happens there. It's quite stupid for me. There's no problem. I mean, I would go there and I have a clock with me. So okay, 2 minutes I'm there, 2 minutes I'm there. And you, that stays here, much wiser than me, would never see me crossing that. If you wait for 2 minutes, you'll see signal from me that gets slower and slower and slower. You'll never see me crossing.
It's something here kind of bothers me because at the end of the day, space-time should be just one manifold, and all observers should spread the same events, but with different coordinates. Well, here you have an example of something that doesn't happen for one person, it does happen for the proper time person.
No, it happens. But you just don't observe that.
You don't know that. But that's the way, right? It's going to get way more confusing now. You just
It's
start.
very confusing. If you stay in infinity and you drop an astronaut into space, at the finite time, even by your perception, is there, but you keep getting messages because as he was crossing, there was slower and slower and slower messages. So you'll keep getting them up to infinity, up to infinite
Essentially,
time, but it doesn't mean you didn't get them.
From my perspective, I never see this.
You never
Person
see. The
crossing
observation is you're correct.
Again, well, your intuition is correct. It's not just intuition, right? I said there is no problem crossing that in a finite proper time. There's no problem. Meaning, for my clock, I could cross this quite okay, and you're right that this may be an issue with our coordinate system. Now, we chose the coordinate system to describe the full space, t, r, theta, and phi. So we mentioned that already when we started to discuss Rothschild solution. Maybe it's a matter of coordinates. Maybe we just chose wrong coordinates. Maybe we could simply use other coordinates. So now is the time to use other coordinates. See where it is heading.
But it's not just a matter that it's not just that you don't see the astronaut getting into the black hole. According to the equations, it never happens. It happens in an infinite amount of time.
Yeah.
So how is it that something happens for one observer and doesn't happen for another observer? It should be the same space-time continuum. The same.
It's a matter of coordinates. Right? I choose the time coordinates. Let's save this question, and I think by the end of, maybe not this lecture because we only have like 15 more minutes, but pretty sure that by the end of Sunday's lecture, you should get an answer. And if you're not yet, that's because it's really confusing and you have to think of it. So we said this is again what is this? This is light ray propagating radially. Okay, and we describe space-time with these four coordinates: t, r, theta, and phi. But let's try to use theta and phi. Forget about them. We're not really interested in them. We're doing things only one dimension right now, so forget about them. And let's introduce new coordinates. So what do? Well, just solve this equation. The t over the r is plus minus 1, so let's solve that. And this is something which you can solve quite easily. That will give you that t is equal to plus minus, call it r star, plus some constant. And r star, it has a name, this is called tortoise itself. Or it is coordinate r star, which is r plus 2gm ln of r over 2gm minus 1. Now it's really straightforward. Just plug it in and solve for the TDR, and you'll see that you get this result. So rather than r, I'm going to use r star, the Tortois coordinate. Again, this is really straightforward.
One not tortoise?
What?
Tortoise, not tortoise.
Tortoise.
Is this
I think
turtle?
it's not Tortois.
It's not.
You're right, tortoise, but I think you're right. I think when you say it sounds okay.
Tortoise is
Tortoise, Tzav, briefly.
Tzav. Yeah.
Tzav.
Tzav is
That's how it's.
Tzav.
I think that when you say it in English, then the correct word is Tortois, but maybe I'm not going to argue with you. Okay. So if I'm replacing now, so replace the regular r with the Tortois coordinate r star, and I write the metric ds squared now as 1 minus 2 gm over r, which is now kept as a function of r star, times minus dt squared plus dr squared, and plus r squared d omega squared. And r is now thought of a function of r star. So that's already quite good, because none of the metric coefficients becomes infinite.
Where's the r squared?
dr star, of course. Thank you. If I draw the light curve, what do I see? This is now r star, and this is t. What would the light curve look like? Exactly, it's a plus minus 1. So where is it going to be plus minus 1? It never closes up. It was a little bit of cheating in a way. Why was there cheating?
Because you have the land that they built. The definition of
Right, I mean, what is when r is equal to 2gm, what is r star? Minus infinity. So really what I did, I just took, right, I just took the bad point, the short radius, and just throw it to infinity. R equal to gm, r star is minus infinity. And obviously this coordinate, I did put here absolute value so that it will be mathematically valid, but really it doesn't make me much physical sense to look at the Tortois coordinate at smaller values than 2g. But because again, you never reach it. You need to go to minus infinity first to reach it. So physically it's not pretty good. Okay, so that was the first step. We did something. Now let's move on to the next step. The next step. Next step is to again redefine the coordinates. So what should I do now? So the next step is now to define again new coordinates, which again are naturally fit into the non-geodesic. So it's going to be u tilde and v tilde. So u tilde is t plus r star, and a v tilde is a t minus r star. So again, if we're talking about infalling r goes down, it goes into the black hole. And then radial means the omega is equal to 0. And null, which is ds is equal to 0. Geodesic. Then what do we have? We have that u tilde is constant, which is quite easy to see, right? Because when you are at radius which is above the Schwarzschild radius, then when r goes down, r star goes down, r decreases, r star decreases, time increases by the same amount here, and so du tilde, which is dt plus dr star, is just a 0. What? Du tilde, u is t plus r. R star. They both have the same g, the same metric. Okay, so du plus dt plus dr are 0, which means that u is constant.
In
That's what I
means
said.
t equals minus r.
Yeah. T is equal to
Minus r star.
Yeah.
Outfalling.
dt is the outgoing. There's infalling and outgoing.
Yes, outgoing
It's
is
going out.
outgoing
V
is
is
t
constant.
equals is v.
Its v will be constant. But we're talking about infalling. U tilde is constant. What? Okay. And then what we do is to replace the time-like coordinate. By the way, when people say time-like, there is one coordinate which has a minus sign in front of it and 3 coordinates with a plus sign in front of it. Any coordinate that has a minus sign is called a time-like. Any coordinate that has a plus sign is called space-like. Just that you know that. So the next step is to replace t with this new coordinate u tilde, and then we write the metric ds squared is a minus 1 minus 2 gm over r du tilde squared. So t is replaced by u, but keep r. Keep r as a coordinate. So this game was just relevant to get u, du, and then we had a plus du tilde dr plus dr du tilde plus r squared du minus. These coordinates, u tilde, r, delta, and phi, they have a name. These are called the Eddington-Finkelstein coordinates. Now you'll see that although g u tilde is equal to 0 when r is equal to 2gm, the determinant of the metric is always positive. Right? So that's or the negative is a minus r to the 4 sine squared theta. Very well behaved. Will behave everywhere. Well, we have everywhere means it's invertible, and simply when r is equal to gm, just have a singularity of the symmetric coordinates. So because it's a well-behaved, we can now extend the range of R to below 2 GM. Every value of R which is greater than 0. So we have before that, so just write extend the range of R to R greater than 0. Now if we again calculate the radial null curve, radial null curve in Eddington-Finkelstein coordinates. So from here, du over dr if it's an infalling, what do we have? 0, because that's how we constructed u. U is not changing. So it's 0 for infalling by construction. And if it's outgoing, right, and again, you just dr is equal to 0. Sorry, radial means omega is equal to 0, so dr can be 0. And then you just have here that du over dr is just 2 minus 2gm over r c squared minus 1. That's for outgoing. Let's draw the light cones in these coordinates. Coordinates are R and u tilde. We have R equal to 0 here. Let's say this would be R equal to gm or c squared. Constant u tilde. How does the light cone look like? If R is very large, infalling du dr is 0. So constant u, that's a flat line. And outgoing u over dr is 2. So it will go something like that. If we are exactly at 2 gm over c squared, what is the infalling? 0. It's always 0. What is the outgoing? What? Infinity. So it will look something like that. And if r is smaller than 2 gm over c squared, go somewhere here. Now it will be smaller, right? So it will be something like that.
Should it be negative?
No. It's outgoing. Let's say it's half. R is smaller than that. So you have 1 minus minus to minus. Yeah, this is the u over the r needs to be smaller than 0. Yeah. Yeah, so it's okay, it's fine. There's no problem. Yeah, it's okay. Go in this direction. There's no problem. It's okay. But what does it mean? That's okay. The way I draw it is correct. What does it mean? So if I have a particle, photon, it's a radial motion that is here. It can move either in following direction, so r gets smaller or r gets larger. Go here or here. Go either away from the center here or towards. But if I'm here, what happens? I can only go in one direction. So all my future directions will take me into smaller r. Right? R is always going to decrease. So once I cross this Schwarzschild radius, 2gm over c squared, right, all future directions inevitably takes me to r equal to 0, to the singularity. Right? And this is for photons, right? So everything, we cannot travel the speed of light, so we must be somewhere within this light can reach it. Right? So if anything happens inside, right, all future directions will be taking it to 0. So what does it mean?
It's impossible to get out of the short.
It's not just impossible to get out. There could potentially happen here various things. Something can happen here. But all future directions will take this inward.
It's impossible to stay in place.
It's also impossible to stay in a place. That's right. Several things. So first, you realize everything that happens here, there's no way to be communicated to the outside world. Right? So that's why.
You can send a signal, right?
If you try to send a signal outward, you can try to send a signal outward, but it will always be taking you inward. Right? Which means that, this is why it has another name, is the event horizon. This is the event horizon. Because all future signals takes you inward. So any event that happens, it could happen, various things could happen here in principle. But we've got no way of knowing, because we're in the outside world. And the second thing you said is also correct. Once you cross this event horizon, all future directions will take you to r equal to 0. So you cannot even stay at the same radius. If you cross that, you're doomed. You're going to fall into the singularity at r equal to 0. That's where the laws of physics as we know them fail. Once you get to a region where the density gets higher than the Planck scale, you don't know what happens. You will die before that, so you don't need to worry. You won't have much time to worry. And if you want to maximize your survival time, what should you do?
Get away from the black hole as they
If
can.
you cross the event horizon, what do? Nothing. Stay on the geodesic. This will be the longest time. Anything you do will take away from the geodesic, will just makes you fall faster. Right? Okay, I think so. continue. I'm already passing out of time because time is flying by. We're having fun. So we said, okay, so since we cannot see inside the event horizon, that's why we call this a black hole. Because nothing that happened inside would send us any signal. So what did we, let's summarize before we go home for the weekend to think of these things. What did we find? We found that our initial suspicion was right? I mean, we cannot reach this black hole because we use coordinates which are not appropriate. That's right. Then, although for observers at infinity, we will never be able to see anything crossing the event horizon. Nothing really prevents anything to cross the event horizon. In fact, as we see, if you're an astronaut and you decide to cross it, you won't even know that you crossed it. But once you cross it, it's a point of no return. There's no way you can get back. There's no way you can send anything on signal back. The only thing that you can do is just wait until you get to the singularity. And the less you do, the longer it will take.
Yeah. You said that anything that takes you away from a geodesic increases, decreases the amount of time it's going to take you to get to the singularity. Why is that exactly? It has to do with minimal time, maximum time.
All right, so okay, I already passed the time. Nobody complained. It's a good sign. Or you didn't notice because you're interested, or you didn't notice because you're too bored. I've got more things to say about that. It's not the end of this, which is important to say. So we'll say that on Sunday. Right, so have a good weekend. I posted the problem set 2 days ago. I don't think I'll post another one today, it's too early, but maybe on Sunday I'll post the next one, just to be sure that we're all aligned. All right. Have a good rest of the day and a good weekend, and we'll see you all on Sunday. 10 a.m. It's slightly early, but I can do it and you can do it as well.
רגע את מה שאמרנו לפני משהו כמו חצי שעה או שעה על זה שבעצם ברגע שאנחנו נכנסים מעבר לשני GM וסקוואר, אנחנו לא, מי שמבחוץ לא יכול לראות את מה שקורה מבפנים, נכון? אז הראינו את זה קודם, כאילו זו עוד דרך פשוט להראות את זה.
זה לא דרך להראות את זה. מה שאנחנו ראינו קודם היה כצופה מבחוץ, אנחנו לעולם לא נראה שמשהו בכלל